So here we're going to take a look at something called a platonic solid. Oops. Also known as a regular polyhedron. Okay. All right. Now, here we have our 5 platonic solids. Right, this one's called a tetrahedron. So here what makes these, or what defines a platonic solid, is that all of their faces are regular polyhedrons. So they're all the same faces. By regular means that like a square, all the sides are equal, as opposed to a rectangle. All right, so our tetrahedron is all equilateral triangles. Let me see here, octahedron. All right, again, equilateral triangles as well. All right, then this one is the dodecahedron. Now here, notice the faces are polygons, pentagons, right? A polygon, but in this case, a pentagon. And the icosahedron, also made up of equilateral triangles. Okay, now what couple of properties. So these are called convex, right? So what that means is if you choose any 2 points that are not on the same plane, so on different faces, when you connect any of those 2 points, that line that connects them is always within the shape, right? So in like a 2-dimensional kind of idea, we can think of something that's convex is if you choose 2 points in that set and that lies completely within that set, or as opposed like something like this that kind of bends over itself, where you can choose 2 points here, right? And when you connect them, not the whole edge doesn't lie inside that set, so that is not convex. Okay. All right. Now, the internal angle formed between any of these faces, all right, has to be less than or equal to 180, or usually less than 180, right, for it to be a solid. Right? If it was completely 180, then it'd be planar, and it won't be a proper solid. Okay, so that's one thing to keep in mind. As another way to think about convex is that the angle that these faces meet has to be less than 180. Okay, and another thing about these 5 platonic solids is that they satisfy Euler's formula, right? The V minus E F, and again, edges are the edges of those polygons. The vertices is where they meet, right? So all 5 of them satisfy Euler's formula, and you can look at the projections here. All right, if you think of it not as a 3D object, but just projecting it, the vertices as the points here, and then the edges as just line segments here. And we can see we can treat them as graphs, connected graphs here. All right. Okay, now, as it turns out, there are actually only of these 5 platonic solids, right? These that we see here, right? Those are the only ones that exist. No other one exists. Now you can have, not that you can't make a solid 3-dimensional object without polygons. You could do that, but you have to use like different polygons, right? Squares and triangles, or polygons and triangles, etc. Right? But the ones that are platonic or made up of the same regular polygon, there are only 5 of those. Okay, so let's try to see why that has to be the case here. Excuse me. Okay, so our theorem here is that there is only 5 platonic solids exist. Okay, so remember, in these platonic solids, each face is identical. Okay, so here, let's take a look at it by cases. Now, I won't outline the whole proof, right? I'll look at the case where it is a triangle, okay? And then I'll generalize it to just an n polygon, right? So here, I'm going to let f, the variable f, be the number of faces. Okay. So the number of edges is going to be 3 times f divided by 2. Okay. Okay. So Euler's formula states that v minus 3f over 2 plus f is equal to 2. All right, now in other words, if I solve for v is 2 plus f over 2. Right. Now each vertex has the same degree. Okay, you can see here why that has to be the case here, since all the faces are the same, right? The vertex, it has this kind of symmetry where each vertex has to have the same degree. Okay, let's call that degree k. Okay, so the edges are whatever the degree is times the number of vertices, but again, that overcounts, so we divide it by 2. And then E is equal to 3f over 2. All right, now setting those equal to each other, we have 3f over 2 equals to kv over 2. All right, and then here, doing a little substitution here, so k will be 3f over v, substituting what we have up here for v. So we get k is equal to 3f over 2 plus f over 2. Getting rid of this complex fraction, we get k is 6f over 4 plus f. Okay. So we have here again, k is the degree of the vertex. So k is some positive integer, right? And the faces are also some positive integer. Okay. Now the degree of the vertex must be at least 3, right? Since we are dealing with a 3-dimensional shape here. So if we think of, right, the vertex, right, the degree has to be 3 because of the vertices that are coming out of it have to be at least 3 shapes in order to get that sharp corner and have a solid corner coming out into 3-dimensional space here. All right, so it has to be at least 3, right? And if we look at here, right, if we think of, well, I can generate this shape, this with triangles, to be an infinite number of faces. I can make it just bigger and bigger, but I'm really bounded by this formula here, right? And as f gets larger and larger, right, possibly infinitely large, well, it can only get as high as 6, right? If we recall our limits here, right? The limit as f goes to infinity of 6f over f plus 4, that's equal to 6, right? So we're limited to the faces to be 3, 4, 5. All right, and it never truly becomes 6. 6 is just the upper bound here. All right, so when k is 3, here, if I plug that in, we say, okay, well, how many faces is that? So we get 6f over 4 plus f. Solving that here, we get 12 plus 3f equals to 6f. And here we get 12 is equal to 3f, or f is equal to 4. Right, and that is our tetrahedron. Right? Look at that here. That is this. 4 equilateral faces. Right? And k is 4. Right? Solving that same equation, we get 8, and that is my octahedron. We get the 8 faces of our equilateral triangles. And then when k is 5, solving that same equation, f is 20, and that gives me my icosahedron, right? 20 faces, right? So that's 3 out of the 5 of them here contain equilateral triangles, and we see the cube here, right? And through a similar process of this kind of proof I'm outlining here, right, where now you'll treat, right, f to be the number of faces here, right, and the edges now will be 4 times f over 2. Excuse me. Okay, now let's generalize here to say, okay, well, we can run through the same proof for the case where it's a triangle, it's a square, right, and it's a pentagon, 5, that is our dodecahedron, right? But that is about as high as it goes, and this is why, right? So let's look at an n-gon, right, where n is greater than or equal to 6. Okay, so n-gon is just a regular polygon with n sides. Okay, and we're going to show here why that is impossible. So the edges will be n times f over 2, right? And again, this over 2 is because they're tiled, right, as a 3-dimensional solid, so each edge is doing double work, right? It's an edge to 2 faces. Okay, so Euler's tells me v minus nf over 2 plus f is equal to 2. Okay, and then solving for v, right, so here, v, you get nf minus 2f over 2. Okay, and as before, each degree has to have the same vertex. We'll call k. So edges are k times v over 2. Right, but edges from before are n times f over 2 as well. So setting this equal to each other, we get n times f over 2 is equal to k over 2, and then v, I'll use this for my v. We get 4, oh, excuse me here, I'm missing a 4 here, 4 plus because of that 2. Okay, so 4 plus 2f minus mf over 2. Okay, and then solving for k, we get 2nf over 4 plus n minus 2 over f. Okay. Okay. Excuse me. Okay, here. So as we see here, what's going to guide here how many, the degree of this is 2n over n minus 2. Right. Okay, and then we see here that as the n-gon gets larger and larger, right, this is going to 2, right, no matter how many faces there are here. And we see that this would be impossible for k to be greater than 6, right? So here, if we say the n is 6, right, so that's 12 over 4, so that's 3, right? So that's not going to work out for us here, since we need it to be of size n, right? So we have this bound here where through this process here that we're bounded by the largest or the biggest polygon that can be made into a platonic solid is this pentagon. Everything else would be impossible. All right, now this is useful in solving, right, and being able to determine if I can make a convex polyhedron. All right, so here, let's say, for example, by just understanding the interplay between the vertices, the edges, and the faces, right? So let's say the question is there a convex polyhedron with 3 triangular and 6 pentagonal faces. Okay. All right. So if we think of this here, 3 triangular faces, so that'd be 9 edges, and then 6 pentagonal faces, so that'd be 6 times 5, so for a total of 39. But again, these edges are doing double work, so when I try to half these, right, I cannot, it has to be an integer, but since 39 is odd, right, that cannot be the case, right? So not an integer. So this type of convex polyhedron will be impossible. Now let's try another example here. All right, is there a convex polyhedron with 3 triangles three triangles, 6 pentagons, and 5 heptagons. All right, so 3 triangles, 3 times 3, plus 6 times 5 pentagons, plus 5 times 7 heptagons, being 7-sided. So doing this, we get 74. So this is at least theoretically possible, since we get edges to be 74 over 2 gives me 37. So 37 possible edges. Okay, so that at least we could see that math is possible. So let's take a look here. So we have 14 faces, right? 3 triangles, 6 pentagons, 9 and 5 heptagons. So we have 14 faces. Now let's take a look at Euler's formula. So Euler states V minus 37 plus 14 is equal to 2. So V is equal to 25. All right. Okay, so that means that through Euler's, the vertex, there has to be at least 25 vertices. Now each vertex must have degree 3 at least in order to have a proper solid. Okay, so maybe it's more. So we're just looking at the bare minimum, and we're going to see that this is not a possibility. All right, so if it has a vertex degree 3, right, well, that means that if there's 25 vertices, we have 25 times 3. Okay, and that gives me 75. Now, what that hints at is that there has to be more than 37 edges, right? So it will not be possible for this to work, right? Because here, again, the vertex 75 divided by 2, again, minimum, so maybe it's 76, but all this tells me is that there has to be more than 37 edges. So what that means that Euler's formula will not be solved, so this type of polyhedron is not possible.